So this is a lecture 17. So currently we are doing some jobs to study or learn how to use G device, which is a device simulator. So previously we have made a certain structure for FinFET, and eventually we will move it to our device simulator and try to perform some device simulation jobs to estimate device performance of that given structure. So for that purpose, today we will just think about the simulation of a long channel MOSFET. So long channel means that we have a relatively long channel length. Yes, so gate length is quite long. So what is the meaning of long? That really depends, but anyway we will have a long channel MOSFET, and I will just show you how can we do this very primitive simulation. Of course, for more advanced device structure, we need include more physical effects, but for a while, just to live with this quite simple structure, long channel MOSFET. So although our structure of interest is of FinFET, but in this lecture, I will just show you very primitive and simplified version of a long channel MOSFET. Please have a look at this one. Here we have oxide, silicon dioxide layer whose thickness is 1.2 nanometer. Okay, so this is somewhat thicker than the currently available one, and maybe this number 1.2 nanometer is the limiting number of our purely silicon dioxide oxide. Below this level, if we reduce the oxide thickness even further, then we cannot make a successful MOSFET, because in that case we can have a really high gate current. So gate should be an isolated channel or isolated terminal, but if we have too thin oxide, then we can have current conduction through this very thin oxide layer. So this is one thing for the limiting value for our oxide layer. And what else? So here we have a channel length of 1000 nanometer. This is corresponding to 1 micrometer. So compared with that number, the minimum number available to this technology, it is much longer. So let's say that we have a minimum number, for example, minimum number of a gate which is acceptable to us. To us means that as a user of that device, well, device performance is more or less acceptable. Let's roughly say that there exists a certain number L min. Then if we go to just twice or 3 times longer than this minimum length scale, then eventually we can quite rapidly approach to the long channel properties. So it is quite easy. It means that in other sense, the occurrence of also short channel effect is quite abrupt. So although we have a certain length scale which can be regarded as long channel regime, but if we enter into the boundary, then rapidly its performance degrades quite significantly. So so in this case, 1 micrometer long channel can be regarded as really a long channel device. And here we have a gate work function. So gate work function, where can we have a gate? Yes, the gate is just placed on top of this channel region, so not shown in this simple schematic, because this although gate itself is a metal, however we do not actually consider the metal itself. So we just consider the boundary between this metal and oxide. So to me or to you, so if we have to draw a gate, then it is just represented as just a line segment in this diagram instead of a full two-dimensional shape, because it is just considering interface. Yes, and its length is 1 micrometer. And substrate, where is substrate? Yes, this the body of our silicon is a substrate, and it is p-type doped, and its doping density is 1.5 times 10 to the 18 per cubic centimeter. So you feel that, oh, it is orders of 10 to the 18. Yes, it is quite high compared with the state of the art devices. We have a much lower doping density for even more advanced devices. As I told you before, the reason why our previous devices have much higher doping density is previously we had no ability to control the threshold voltage with work function engineering. So work function was more or less given, and there was only one single work function for one single type. So if we have n MOSFET, then we have a certain work function, and if we have a p-type MOSFET, then we have another work function suitable for that device. So therefore, we had to control the substrate doping. We have to change the substrate doping to control threshold voltage. That's the reason why we have quite a high density of substrate doping, and that introduces a lot of problems in the variability case, because we used substrate doping as a main knob to control threshold voltage. If we slightly increase substrate doping, or if we reduce slightly this substrate doping, that is directly reflected in the fluctuation of threshold voltage, which is not acceptable at that time. So that is a very difficult situation at that time. So that's the reason why we have moved into the FinFET era, because FinFET has better gate controllability, so we can have a much better control for variability. Okay, and also we will use VDD equal to 1.2 volt. So nowadays we are using 0.7 volt, so 1.2 volt is somewhat higher than 0.7. So please regard this one as a quite old time MOSFET. Okay. So also, since it is so highly doped, so just a short distance like 120 nanometer is enough to consider the entire device structure. Of course, the actual thickness of this p-type or p-well is much deeper. So it is orders of several hundred nanometer or even micrometer scale. However, we can just consider just top a few nanometer or few hundred nanometer safely to consider electrical property of this system. Okay, so now let me just show you how I did structure generation. So eventually, when we have a FinFET, then we will just take the FinFET structure generated from Armstrong graphite directly. But for a while, we'll just draw something, and that is related with this structure generation part. So since the oxide thickness is 1.2 nanometer, we just limit 1.2 nanometer uniform spacing along vertical direction. So this is vertical direction, and we have just 1.2 nanometer minimum distance. It means that we assign just one single interval for our oxide layer. So usually what we have to do is introduce more layers for to have quite a fine resolution for oxide capacitance. However, in this case, we just assign one single layer. Yes, so our calculation cannot be quite accurate, but actually it's just okay. And how about the spacing along the lateral direction? Lateral direction here means that this horizontal one. In this case, we have used 5 nanometer, and since our channel is just 1000 nanometer, so it means that at least for channel region, we have already assigned 200 points or 200 intervals along lateral direction. Of course, please note that our entire system does not contain only this intrinsic channel region. Also, we have to consider this source and of course drain. So we have to have a certain margin. So our lateral points are about 221. So 200s are assigned, or 201 were assigned to this channel region, and additional 20 is assigned to this left source and right drain. And this 102, that is corresponding to our vertical direction. And now we have the number like 22,000 point. Well, 22,000 point in the device simulation, is it enough or not? So nowadays we are simulating much larger number of grid points in reality, because the structure itself is three-dimensional. But please note that this is a really simple structure, just a two-dimensional structure. So for that simple structure, spending 22,000 points, it is like a waste of our resources. But so instead of introducing more advanced features of this program, I will just give you just a uniform spacing along vertical direction and lateral direction. So although your simulation can be a little bit slow, but just live with it. So you can wait for additional minutes, then you will have the answer. And also another one is a source and drain doping profile are usually modeled with a Gaussian profile. Gaussian profile means that now here we have certain, so usually we have a spacer in real case, and this spacer is used as a mask for ion implantation. So on top of this spacer formation, now ions are implanted from top. Then of course they have certain kinetic energy, and now their major movement direction is of course this vertical direction. Yes, so simply speaking, it's like a meteor. So it is coming into the earth and it makes a certain bombardment, and now it just move into deep inside our earth. It is ion implantation. However, after everything is just over, then can we expect this kind of a profile? So all of our injected ions are found in this box. Actually, it's not, because when an ion is coming into this already existing silicon network crystal structure, then it can experience certain sequence of collisions, not just a single collision, but interaction between all of silicon atoms. So direction itself is not just unidirectional, so it can change its direction. Of course, this vertical one is a major one, but also we can think about the lateral diffusion. So if we say something, if we inject one single ion many times at exactly same point, then we can actually trace its trajectory. For example, that can be this one. This kind of several injection implantation can be uh, uh, done, and after that what we can say is, do we have 100% of a probability to find it only that injection point? Actually not. So we will have a certain widely spreaded distribution of its or their lateral position. So simply speaking, although we have made this vertical injection, but in reality we have a certain broadening toward this lateral direction. So that's the reason why our doping profile is usually modeled as a Gaussian profile instead of this box-like one. However, in this example, in this simple example, we just assume abrupt junction and just to say that there exists a certain box. Gaussian profile is also assumed even along this vertical direction. Also along this vertical direction, we have most probable depths of injection. Yes, maybe this is the average depth of penetration. However, there is no certain way to make it exactly at, for example, 10 nanometer. We cannot stop them exactly at 10 nanometer. In average, they can stop at 10 nanometer, but some of them was lucky and go to deep inside this substrate, and some of them is just hanging around this substrate, and it is found much closer from the interface. So there also exists a certain vertical profile, and in its simplest form we use a Gaussian profile. And if we consider more realistic one, then we have more tailored models for vertical penetration. So that is also found in literature. But anyway, in this example, we will consider quite a simple box-like shape for our doping profile. Although we are using this simply highly idealized shape, but please understand, design of a doping profile is one of the most important design factors for our device performance, because when we have a certain device who actually decide the actual channel length, then maybe you can answer this way. Okay, there exists a certain gate, and this is metal. So the physical length of this metal really determines the length of our transistor. However, this is not exactly 100% correct, because in this case actually we have end of our source and end of our drain. Up to this point we can have so many electrons, and up to this point we have so many electrons, and only the part underneath gate, and at the same time without much n-type dopant, that can be regarded as the channel region. Okay, so let's say that unfortunately you have made some mistakes in your doping control. So say that instead of your desirable point, but you have a certain variation of your source profile, so it goes deeper into the channel region, then what will happen? In this case, your effective channel length just shortened by amount of this fluctuation. So then you will find that although you try to make a certain device, but seems to be your device suffer from short channel effect. So you saw that I have a sufficient margin for this device, but your device shows some quite much degraded properties, and such kind of a bad effect comes in. So this doping profile, so source drain doping profile control is critically important. Even nowadays, even as of 2025, this one is critically important, because nowadays and in the coming future, eventually we will have the gate length of around 12 nanometer. That will be the ultimate value of our transistor, silicon transistors channel length. Maybe that is the more or less agreed value for ultimate channel length. Of course, in the last year, IDM and some VLSI, so companies just have shown that we can actually reduce the channel length down to 6 nanometer. Even with the 6 nanometer channel length, we can have a device working properly. However, that does not say that we can start the mass production of a 6 nanometer long channel device. One champion device can survive, but that does not mean that you are allowed to do it with billion and several billion transistors. So 12 nanometer is regarded as the ultimate goal. And yes, now you have a 12 nanometer. And how about source and drain? In this case, you have a certain doping density and doping density, and eventually it starts to drop. And yes, also it starts to drop, and the speed of reduction, speed of decay is just measured as this one. In order to have 10 times smaller doping density, how long distance is required? That is used. Of course, I'm not saying that if we just strictly believe this one means that, let's say that if this is 2, and say that starting 10 to the 20 per cubic centimeter, it means that after 2 nanometer, we have 10 to the 19. After another 2 nanometer, we have 10 to the 18. And after another 2 nanometer, we will have 10 to the 17. So if we just draw logarithmic graph as a function of a position, then we will have just a straight line. Of course, it's not. So actually we have, as I told you before, it's a more or less a Gaussian profile. But if we have doping density down to 10 to the 17, 16, 15, actually they are not counted as a valuable number for doping density. Only the numbers like 18, 19, 20, they are important for doping profile. So simply means that this number is just showing some local slope of our Gaussian profile or doping profile nearby the peak. And in this case, the typical number we have right now is around 2 point something. So it means that if we proceed 2 over 3 nanometer, then we have 10 times smaller doping density. So now if we have a slight difference in its shape, then what will happen? Let's say that this is corresponding to the 2 nanometer per decade, and if it becomes 1 nanometer per decade, what will happen? We will have a much steeper decrease of doping profile. And if we have 4 nanometer per decade, so it means that we have a much graded decay of our doping profile. Then you may find significant performance difference between these ones. If we have this abrupt one, so that will be the best to suppress short channel effect. And if we have this graded or quite a smooth transition from N-type to P-type, then we will have very severe short channel effect, because although our drone gate length is 12 nanometer, but beneath of that drone gate, we have a considerable amount of source and drain entered into this channel region. So we have we have a very short channel device which is not acceptable. So we wanted to reduce this doping gradient as much as possible. However, how can you reduce this doping gradient or increase doping gradient? So it means that first of all, you have to make initially you have to make a very abrupt junction, almost abrupt one. After that, when you activate this source and drain, you have to minimize the diffusion of your dopant atoms. So there is 2 different goals. You wanted to activate them, and also you wanted to suppress their diffusion. Their diffusion should be minimized. It means that in order to activate this source and drain, we must apply heat, quite a high temperature. How high? It is around 1000 degrees Celsius. At the same time, we must ask them not to move, just to stay there and just to become active dopants. So this is a quite significant challenge. So what we do right now is just to apply a impulse of heat. Within very short time, orders of seconds, we increase temperature from certain room temperature to 1000 Celsius. After a few seconds, we just cool it down. It means that they have sufficient energy to just take their desirable position, atomic position inside the silicon crystal, but they have no time to move or diffuse over entire silicon crystal system. So that is we do. And nowadays, even this seconds long anneal, called as rapid thermal annealing. Rapid thermal annealing seems to be too long, so nowadays we are using laser to anneal our source and drain. Laser can be controlled much shorter, and just to expose laser beam, then it gains certain energy and it just takes the desirable position. However, now laser is gone, so it loses its energy and doesn't move. So anyway, this is critically important in our actual case, but let's come back. We will just use abrupt junction. But please remember that in reality, junction profile design is critically important to have working device. Okay, so now using this map maker routine, so we will just make a simple structure. Please just type these lines without any mistakes. So I'm quite sure we can make typos. Then if you make typos, then you will destroy this exercise. So please do not make this procedure. And intentionally I made a three-dimensional structure. However, although we are considering planar MOSFET, we introduce a three-dimensional structure, and that is along Z direction. Along Z direction, we just introduce only 2 points. So its position is Z equal to 0 and Z equal to 1 micrometer. So this is just uniform, and nothing has changed along Z direction, and only we have variable physical quantities along X and Y. X direction is vertical direction, and if we have an increasing X coordinate, it is corresponding to deep substrate. So if it is close to number 0, and we have an interface. Okay, so the interface is around 0 nanometer in our X position, and deep substrate is around 120 nanometer in our X position. And now we have a certain length scale along Y direction, and in the case of Y direction, it starts from negative 550 nanometer and it ends at a positive 550 nanometer. So it means that our Y0 or X0 don't have to be exactly 0. So you can see that our X0 is negative 1.2 nanometer, and Y0 starts from minus 550. So you can just parallel shift everywhere. So it's just okay, because you will have just a shifted structure. For example, in this case, I just made this kind of thing. So Z starts from 0 to 1 micrometer, but you are just free to set it as like a minus 0.5 micrometer, and it ends at 0.5 micrometer. Then what happens? No change at all your simulation result, and you just shift it to this direction, Z direction. And now here you have a certain specification, so I hope that you can easily understand what is going on. And please note that although in this case we have used position, nanometer, or micrometer, however, now in this specification, always we specify certain position with index. So now we have to index integer numbers to specify certain position. So most of our device structure is assigned as silicon, and only the top one layer is corresponding to this one. Yes. So 0 to 1 means that starting from minus 1.2 nanometer and ends at 0 nanometer, this one single layer is assigned as insulator, and all other up to 120 nanometer, it is assigned to semiconductor in this case. And for semiconductor region, we can assign doping, and this is just a box-like way to assign profile. And you can see that for source and drain, we have assumed that 2 times 10 to the 20 per cubic centimeter, and for substrate we have used 1.5 times 10 to the 18 per cubic centimeter. But here we have one thing to be a little bit careful. Here we have a negative sign, and this negative sign is reserved for p-type dopant, and positive sign is reserved for n-type dopant. Later, if you wanted to simulate a p-type dopant, then what you have to do is, instead of this negative and positive combination, you have to say positive and negative. Then you will have a different doping polarity suitable for your p MOSFET. And here we have a contact specification, and source, gate, drain, body are assigned, so please just type them. Then now you will have this structure. So this is the structure you can see. Since this is a really long channel, so this length scale is corresponding to 1 micrometer, and we have a relatively short 50 nanometer and 50 nanometer. And here we have a substrate and source and drain. Then where can you find the gate? If you see clearly, then you can see here a purple line. Then this is corresponding to the gate. Then where can you find the substrate? Yes, also you can see similar purple line bottom. That is corresponding to the substrate contact to fix the body potential. Then where do we have a source and drain? In this implementation, I'm not quite sure you can see clearly. Here we have a very short segment, and this is corresponding to the source, and here we have a very short segment here that is corresponding to the drain contact. Of course, if we draw it really realistic, then what we have to do is like this. Here we have certain well, n plus well, which was formulated by ion implantation. Actually, what we are observing right now is just a half of it. So this half is drawn here. And where can you have the real metal contact? Of course, on top of this N well, we will draw, or we will make a certain metal, and this the metal and N plus resin interface. This one is working as the real contact between metal and our silicon N plus resin. However, in this case, we just assign the side point as a source contact. It means that instead of this one, I'm saying that maybe this one, or depending on its length, this one is regarded as the position of a source contact. Is it acceptable or not? So it is simply because in this long channel device, the position of setting of a source and drain contact doesn't matter, because our devices are so long and everything is just determined by this channel reason. However, please be careful. This is just a classroom exercise. In reality, nowadays, the contact itself determines much or quite a lot of portion of our current conduction. So it should be carefully designed, or realistic way we have to do it. Well, now let's load the structure. You have done it already in our previous example for PN junction. So just to repeat it again. So you just load it, and so the mandatory effective intrinsic carrier density, so it means that bandgap narrowing should be specified. Of course, if you want, and then you can say additional properties. So for example, mobility, recombination, or other kinds of physical models can be added here. But anyway, this bandgap narrowing model is the mandatory one, so you must add it. Without this one, your simulation would not go properly. And in this case, a little difference can be observed here. Previously, we had no such statement, electrode, but now we must add this electrode statement because now we have gate. It is special because in many cases, without this electrode, usually we treat our contact as an ohmic contact. So the ideal contact to exchange the electrons or holes through that contact. However, in the case of gate, it is not attached to the silicon area. It is attached to just insulator, and it does not communicate or exchange their electrons or holes. It just provides a certain potential reference to our system. So for this special contact called as a gate, we must specify work function. So for 0.3, that number is corresponding to our previous value shown here. For example, if you wanted to simulate instead of this N MOSFET, I wanted to also try to simulate the P MOSFET, then you must change the proper work function. For example, let's say that 5.0 eV. This is a somewhat high value, but anyway, let's live with one. Then if you wanted to change 5.0 EV, then in this case, in your loading statement, you must say this should be 5.0 EV. So this is required for your MOSFET simulation. Then you can ask me this question. Well, work function is a property of a material. Then why we have to individually specify this work function? If we have a certain material, then maybe instead of specifying it in our simulation code, maybe simulator itself just determines the work function, and so that can be a valid question. However, work function is actually not a property of our material itself, but it should be regarded as property of our interface between our insulator region and our gate stack. That is the point. So maybe you remember our previous lecture. So let me just come back to our previous lecture. Maybe this one. I'm not that sure. Oh, here. Now you can see that this one. Here, maybe you remember we have thought about titanium aluminum nitride. So by controlling the aluminum portion, we can control the work function. That was the lesson we have studied in second previous lecture. However, you can see certain specification here on hafnium oxide. It means that the work function of titanium nitride is different when it is placed on hafnium oxide or other different materials. So this work function should be regarded as interface quantity instead of its bulk quantity. So simply speaking, let me just come back. So that's the reason why, depending on some the trivial detail of a process, the work function itself can change quite a lot. So you should not fix it as a fixed value, because its consequence is so direct. If we change work function, it just parallel shift our IV characteristics. So without calibrating the work function properly, we never able to match the observed IV characteristics. So we should allow the freedom to calibrate work function here. Okay. So let's go to. So then the remaining part is just same as before. I'm just showing you the completeness of my lecture material, so you can just type them. Now we have two voltage sources. Previously we had one voltage source to apply another voltage, but now we have to have separate voltage sources for gate biasing and drain biasing. Yes, let's introduce two of them and connect this circuit. Let me just once again draw the circuit schematic. So now in the first line we have ground, and second one we have MOSFET, and this MOSFET has a source. That source is connected to the ground, and it has input and gate, and it is connected to the input, and drain, it is connected to output, and finally it has body, and its body is connected to, once again, its gate. So we are done with MOSFET. However, what is this in and what is this out? That should be specified in this part. In this case, we have another voltage source. Yes, and it has two contact, 0 and 1. 0 and 1. And this 0 is connected to the ground, and 1 is connected to in. Quite similarly, we have another one called as VD, and it has also 0 and 1. Its 0 is connected to the ground, and its 1 is connected to output. So you can easily understand, although it is lengthy, but it is just showing that simple circuit test bench to apply gate voltage and drain voltage. If you remember correctly, what we can do in this system is just to change the magnitude of electromotive force for this VG, gate 1, and VD, and by changing its value, then we can change the gate voltage and drain voltage by this connection and this connection. So that is shown here. Now let's go to the equilibrium solution. In the case of equilibrium solution, we must declare the nonlinear Poisson equation here, and by calling this nonlinear Poisson equation, we can solve this equilibrium system. Then this one just shows hole density, so you can see it H density. When you draw H density, you will find this graph, and usually the default color map just shows that higher one is red colored and lower one is blue colored. So in this case, now you can see that there are a lot of holes in substrate. What is it? Because this is p-type substrate, it is quite obvious that we have a lot of holes in its natural situation. However, what is it? This is corresponding to the depletion. Here, beyond this point, we have almost no hole at all. And why that happens? Because here we have a gate, and here we have n plus region. So this n plus region just to push away our holes. That's the reason why we have a depletion here, and also gate voltage just to push our holes. So we have a depletion layer, and underneath source region we have also depletion layer. It can be calculated, and please watch it by your own exercise. And now we can also assign drift diffusion model for non-zero bias condition, and yes, also gate terminal quantity and drain terminal quantities are required to draw your IV characteristics. So now let's just perform. In the case of a MOSFET, compared with the PN junction, we should be careful because previously PN junction we had just one active terminal, anode. Then we had only one active current, anode current. Anode current versus anode voltage, that was enough to have full information about its DC characteristics. But in this case, we have now gate and drain, two different ones. So the important quantities are like this: gate voltage, drain voltage, and drain current. These three quantities are important quantities. Yes, source current is just a minus of drain current, quite similar, and we assume that gate current is quite close to zero, and also our substrate current can be small. So of course we have a certain amount of current. However, it can be regarded as just reverse current of source body junction and drain body junction. So drain current itself, the output current is the single valued. There is no other current, but now we have two different input parameters: voltage and gate voltage and drain voltage. So when we draw certain quantities, ID as a function of VG or ID as a function of VD, we can have two different flavors, and usually this kind of thing is called as input property, and this one is called as output property, because gate voltage is regarded as input voltage and drain voltage is regarded as output voltage. So that's the reason why we call it as input characteristics and output characteristics. In this slide, we are just showing the input characteristics calculation. For that purpose, when we change our gate voltage, we must have a fixed value for drain voltage. So before starting increasing or changing gate voltage, first of all, we have to arrive at that target value of drain voltage. So before starting changing gate voltage, first increase drain voltage. Up to what? Up to a small number or higher value. For example, in this case, usually what we do is drain voltage equal to or close to zero or VDD. These two quantities are used. What is small? Small, sometimes people use 50 millivolt, yes, in this case, or 10 millivolt corresponding to 0.01, even 1 millivolt. It's up to you. So actually not up to you only, but if you are belonging to a certain group, research group or industrial research team, then they have their own convention. Our small voltage, drain small voltage is fixed to something, then you must adopt that number. Anyway, in this case, I just adopt 50 millivolt as a linear one and apply VDD. If you wanted to have VDD, then of course you can say 1.2 volt. But please be careful. If you just naively say 1.2 in this case and run your simulation, I'm afraid that your simulation will fail because in this case you just initial step equal to 1.0. It means that just directly try to solve your target value. Then can you guarantee that your simulation from 0 to 1.2 gives you the correct successful result? There is no guarantee for that. So if you wanted to introduce this 1.2 value, then you have to reduce this initial value and also introduce certain specification of a max step and min step. So I will just leave it to you. So try to find out correct value. The rule of thumb is if you make very small numbers for this max step and min step, then more or less you are guaranteed to have a successful result. But at the same time, it means that you have to wait for a long time. For example, you were quite successful. So you were quite successful with your max step equal to 0.01. Well, you are happy, but to be sure, you wanted to introduce 0.001. Then what will happen? Yes, once again, you will have the converged solution, but you have to wait 10 times longer because your simulator will introduce 10 times more intermediate bias point to calculate your target voltage solution. So then why don't you just, instead of that, why don't you try 0.1? Yes, if that helps and if that works, that is much better than 0.01. 10 times less number of bias points. But who can say certainly that your trial will be successful? That's the problem. So it is to us, before starting a certain simulation job, we cannot guarantee that this parameter set stepping is enough tight to guarantee our convergence or not. So that's the problem. So usually we become a little bit conservative in this sense. We start a little bit tight value, then wait for a while, then we'll get the solution. Okay, so let's assume that now you have successfully done this drain lamping. However, this drain lamping, during this drain lamping, you may ask me this question: what is the value of Vg? That is initially set to be 0 volt. So we are just changing the drain voltage and gate voltage equal to 0. And from now on, in this second solve routine, now we increase the value of gate voltage source up to 1.2 volt with max step equal to 0.01. It means that the maximum voltage change allowed to this gate voltage is just 12 millivolt. Quite a small value is allowed, and you will see that actually this is a little bit too tight. And if you wanted to shorten your simulation time, of course you can increase it. But well, just to play with these numbers, then you will find that the life is not that easy in this sense. Well, anyway, then after this kind of job is over, then you have a certain CSV file, and please draw it. Then when you draw it, you will have two different lines, because yes, previously you tried 50 millivolt, and if you change this number into this number to 1.2, then you will have another line corresponding to this one, VD equal to 1.2. Since you have applied much higher drain voltage to your drain, it is certain that you have a much higher drain current at a given gate voltage. That is quite obvious. So now you have this one, and since this drain voltage is so low, usually we interpret it as a linear property, and since this is just equal to VDD, so we treat it or consider it as saturation property. Beyond the threshold voltage, we are now observing the saturation current and linear current. Okay, so when you have a linear current, what we can see is actually a certain line, almost a straight line. However, in reality, it's not. In reality, we can have some usually degraded slope of this curve. So not this straight line. Usually, what we observe is like this one. And this reduced slope is usually attributed to the reduction of electron mobility. Unfortunately, if we apply higher and higher gate voltage, it means that we wanted to get more and more electrons, and we wanted to get higher drain current. But unfortunately, there is a tendency to the reduced electron mobility when we apply higher gate voltage. So although we increase, or although we collect more electrons, but their speed is reduced. So that's the reason why we have a reduced slope in this case. Well, so anyway, now we have two different curves. But the real importance of this curve is not drawn in this scale, but it is seen in this semi-logarithmic scale. In my opinion, actually, if we have to select only one single graph from MOSFET's IV characteristics, this is the one we have to draw. So, drain current as a function of gate voltage, but with two different gate voltages. Because from this curve you can find many important points. One is this point. In this case, what is gate voltage? Gate voltage equal to VDD. And what is drain voltage? Drain voltage is also VDD. So simply speaking, this curve, this point, just gives you on current of your transistor. So on current is the one to be maximized for higher performance. So this one clearly gives you I on. And also another one you have to be careful is this one. Here you can have VG equal to 0 volt, so you wanted to try shut down your transistor, but drain voltage equal to VDD. If this transistor is completely governed by or controlled by gate voltage only, then even though we have very high drain voltage, Ig should be 0 or quite close to 0. But in reality, we have certain undesirable number of current here, and this one is usually called as off current. So are you with me? So these two numbers are most important. Means that ion, this is corresponding to the performance of your transistor. If this number is higher, then we call it as a high performance device. And we have I-op. If this number is low, then we call it as low power device, because when we turn the transistor off, it does not spend a lot of standby power. So these two quantities are most important quantities, and this semi-logarithmic graph gives us this feature quite clearly. If you take just a linear graph, then what will happen? You can clearly see this ion, but at the same time, you cannot see this op current, because the op current is so small. So when you draw in linear scale, it just drawn as a number 0. So you can see it here. And another important one, which can be seen in this graph, is this one here. Now you can see two graphs. One graph with VDD and one graph with quite a small voltage, drain voltage. And when you have a look at these two curves, they are quite close. However, you can see there is a parallel shift of this one graph. This right positioned one, that is corresponding to 0.05, and left positioned one, that is VDD. And this is just happens because same device, so there is no changes in its device structure, only increasing drain voltage, and now threshold voltage of this transistor is reduced. So this is very much undesirable phenomena, and actually this dibble is the most important quantity we have to be careful when we talk about short channel effect. If this dibble is so high, what is so high? I have seen so many values about dibble values, but it is clear that if you have 1 millivolt per decade, that really destroy everything. So it is not acceptable. Then maybe you can ask me this question: 90, is it acceptable? Actually not. Actually, we wanted to have the numbers like 50, 60, 40. These values are regarded as acceptable value for industrial level mass production devices. So I wanted to ask you this one once again. Since you are undergraduate students or senior members of you are graduate students or senior undergraduate students, maybe you will be involved with some device researches. Then please ask yourself, what is dibble of my device? If dibble of your device is not like this number, but I can see so many papers whose dibble is volt per volt or 10 volt per volt. So if you have this kind of numbers, it cannot be actually used. So meaningless of course, in sense of mass production. In terms of research, okay, it's just okay. And finally, let me just conclude my today's lecture with the final quantity. We have slope itself here. Although these two graphs share because they are parallel shifted, but if we have different device, then we can have different slopes. Yes, or we can have even or mild increase. This slope is corresponding to sub-threshold slope, and this slope is critically important. This slope nowadays should be quite close to 60 millivolt per decade. If this one is much higher than 60, then also it cannot survive. Previously, in the case of a planar MOSFET, actually the numbers, acceptable number was around 100 millivolt per decade. More or less this value was regarded as a criterion for acceptable. 90, 80 regarded as a quite a good number. But in the case of a FinFET, nanosheet FET, nowadays we are now talking about many different multi-gate structures. In that case, there is no exception. We should have the value quite close to 60. 70 is acceptable, but 80, I have not seen the numbers like 80. Okay, so I have prepared a few more slides, but for a while, just to stop here. And my suggestion is you don't have the official homework today. However, when you go to the end of our lecture material, then we have to draw many things using this one. So instead of just wasting your time, just start homework 18. So homework 18 will be just a continuation of this one. Just to follow the steps shown here and type my example file without any typo. One single typo will destroy your input code. So without any typo, just type and just try to reproduce my curves by your own hands. Okay, do you have any question? Okay, if not, then let me conclude.